Okay, so today and tomorrow we will look at data structures for the where you can support these operations in constant time. If I tell you this extra information that the range is a fixed universe, okay. Yeah, so it's a characteristic vector of the set. So S is a set you want to represent. I represent the characteristic vector of the set. So I can have an array which simply says with A of I equal to 1 if I is in S and 0 otherwise. Okay, now so why can you support these operations in constant time here? So if I want to do membership, I want to know whether X is in the set, I just go to the ith location, and if I want to know I is in the set, I go to the ith location, and if it's 1 I know it's there, if it's 0 I know it's not there. Similarly, if I want to insert it, go to the ith location, flip that bit. If I want to leave it, delete it, flip that bit from 1 to 0. Okay, so all of them can be done in constant time, but what is the drawback of this approach? Right. Space is an issue, right? So if M is really large, then I mean, typically we know M in any application. You know that the values you are storing is at most 1 word of the computer or 2 words of the computer. So it's not that you don't know M, but M can be really large, and you can't afford to spend space proportional to the universe size. Okay. So this is in the sense that you can support the operation in constant time. The problem is in the space. So the question people asked in 1970s is there a structure where I can use space? Okay, so the drawback, so time is constant and space is M, and the question space order n, I want to use space proportional to the number of elements in the set, not proportional to the size of the universe, and still support operations in constant time. So today we will see yes, but constant expected time. And tomorrow constant worst case time we will see, but for membership alone. I mean, this can be improved, but tomorrow we will see only for membership. So assuming a static set. Okay. Don't worry about what all these means. We'll look at that tomorrow. But so the structure we'll look at tomorrow is, suppose I give you the set in advance and say here is the set I want to represent. You do whatever pre-processing you want, but I want the membership to be done in constant time. Is that possible? Okay. and there is a very elegant structure which says that yes, that is possible, and that is what we will look at tomorrow. Okay. Have a sense of what expected time means, but we will make things precise. So, that we are interested in, so universe U out of which there is some set which I want to represent, and I want to represent in a table so I want to actually map this entire universe into this. So I mean, you know what I'm driving at, right? I'm looking for a function, a hash function, which somehow brings down the universe size to something small. But when it comes to this set which I want to represent, I want to make sure that this gets mapped injectively. That's the tomorrow's problem. Today I want to make sure that not too many elements get mapped to the same location. Okay. So let's get started. So one way to deal with this fact that I have a lot of space here is that I think of some function h which maps the universe to, I'm interested in the space order n, let's say some a table P whose size is some order n. That's what I'm interested in. I want to take the universe. For every element in the universe, I'm going to point to a location in the table. So, natural thing to deal with the space issue is that I somehow map this universe into a smaller size set, then I'm going to get, what sort of problems do I get? So let's say somehow I come up with some function which takes this universe and maps it to a table T, and now store element x of the set you want to represent in the location h of x. Okay. So for every element there is an image which takes you to a table of size order, and suppose I have such a function. Okay. Now here is my solution to the dictionary problem. You want to store the element x. H of x is a value in that range, so you go and store it. And whenever you want to know whether x is there, apply h of x, go to that location. If x is there, you say yes, otherwise no. What will be a problem here? Many to one function, right? So more than one element gets mapped to the same location. That gives rise to what's called a collision. Collision is a pair x, y, x not equal to y, into x. Okay, so we live with the fact that we are taking a large domain and map it to a smaller size table, so there will be collisions. So first let's figure out how do we deal with collisions. There are multiple ways of dealing with collisions. So these functions are called hash functions. So dealing with collisions, one approach is called chaining, which is the simplest, and we will start using this. Store all elements x such that h of x is equal to I in a linked list. so we'll figure out what the size of the table I want is. But essentially what I'm saying is whenever I have an x, I map it to h of x, it takes you to this table T, and let's say it takes me to this location. There is some other y which also takes you to location. You create a linked list here and store them. So basically you store it at the beginning of the list. Okay, so modulo the fact that I haven't told you what the table size is, now I have a clean data structure solution, which is that I take every element, map it to a location in this between 0 to t minus 1, and all elements that get mapped just go there. And when I want to search for an element, apply this h of x, it takes me to the location, search in that linked list. When I want to insert, again do the same thing, search in that linked list, make sure it's not there and go and insert it. When I want to delete it, it's very symmetric, go there and delete it from the linked list. Right? Now what would be the worst case time? Worst case time. And it's possible that all elements of your set get into one location. So the search will boil down to searching in a linked list. You have to do a sequential search, you will figure that out, right? So the worst case, it could be as bad as the size of the set. Okay. So how do we now, as I said, today's plan is to improve on the expected time. So expected time is a function of a lot of things. It's a function of your function h, right? How good the function is. It's a function of how the elements are distributed, right? So suppose I think of a function as simple as following. Okay. Let's say so u is 0 to m minus 1 universe, and this is 0 to t minus 1. Let's figure out what the relationship between t and n is. Now, suppose I just think of a function which simply says, here is a x mod t. Okay, assume we're, I've already assumed the universe is integers in the range 0 to m minus 1. I just do a mod t, then the range is clear. It gives you a value between 0 and t minus 1. Now, such a function is good on the expected sense if your input, I know, is sort of distributed, that there's no bias on the input. It's, in terms of the mod values, input is reasonably distributed. Then, if you take an element, it has an equal chance of going into any of the locations. If the value you are getting in is equal chance of any of the mod t, you suppose it's uniformly at any of the locations, then it will, this is a reasonable nice function. But then it's a reasonable under the assumption that your distribution of the input is reasonable. Okay. Now, one of the things we want to do in randomized computation, randomized algorithms, is take the randomness assumption from the input and build it into the algorithm. Okay. Do you understand what I'm saying? Do you understand the statement? Let's look at it in the context of quicksort. Okay. You've seen this over and over again, hopefully, right? So there are two versions of quicksort. One algorithm says, take the first element as the pivot, do a partitioning, recurse. Okay, so I'm giving you n elements. I just take the first element as a pivot, partition all elements with respect to that as those less than, greater than, and recurse. Okay. What is its running time in the worst case? N square. And what is its running time on the average? What does on the average mean? Okay. Yeah, expected over what? Expectation is all about average. Average is all about certain average over certain distribution. So you average over a bunch of things and take that average. What is that bunch of things we're talking?
Permutation.
All permutations of the input, right? So if you run over all permutations of the input, so if your input is 1, 2, 3, 4, 5 to n, and you do this deterministic algorithm which simply says pick the first element as a pivot and partition, you compute the running time, change the permutation, compute the running time, change the permutation, compute the running time, and do an average. That average is n log n. Okay. So why is this good? This is good if your input is random. You have no bias on the input, your input permutation. So under all possible, if all permutations are equally likely, then this gives you an n log n running time. But in practice, in reality, your input may not be random. Okay. So suppose you're running your quick sort on an application where it turns out that most of the time the input is almost sorted. Okay. Now here, you have a problem. Okay. The average running time is over all possible permutations of the input. But if all permutations are not equally likely, then this algorithm, this deterministic algorithm, fares badly. Okay. So now how do you deal with it? What do you do?
Take any random element.
Random
Take any random element
as the pivot. Now this is building randomness into your algorithm. Okay. Remember the first algorithm I said, pick the first element as the pivot, partition, recurse. There is no randomness at all. It's a deterministic algorithm. Algorithm is not doing any coin tossing. It is not consulting any random number. It is a deterministic algorithm. The analysis is overall permutations. Okay. Now it has this uncomforting thing that if all inputs are not equally likely, it can become bad. So what do? We build the randomness into the algorithm. I don't care how the input is. If I pick a random pivot, so every time I don't pick the first element as a pivot, I just consult a random number. It gives me some value between 1 and n. I pick a random pivot and then do a partitioning. It has an expected running time of n log n. Now what is this average over? All possible?
All possible
Choices for the random value. Okay, it is not all possible permutations of the input, because for every input, so this is I want you to understand this. This is the big, crux of building randomization into the algorithm. In one case, I had a deterministic algorithm. We average it over all possible permutations. We compute the average, and that's order n log. In the other case, for every input, I have, the randomness. The random choice could be the first element, second element, third element. You don't know what the random number throws out. And then I do a partitioning, and even in every step of the partitioning, there is a randomness. Now you do average over all possible choices of this randomness. That average is n log n. Which means sometimes for certain choices this might be taking n square. Okay, but that's not based on the input. For every input, there are certain choices the random number throws out, for which the algorithm may take n square, but that's not based on the input. Okay, so for every input you have this problem that for small number of very small probability at which it's going to take n square, but this probability is over the choices of the random number you are using in the algorithm. Whereas here the probability is over your input, under which you have no control. Whereas this is, if you assume there is a pure random number generator that gives you, or a pseudo random number generator, then so both cases there is an assumption here. Here the assumption is over all possible input permutations. Here the assumption is over all choices of the random number generator. But this assumption is reasonable, and this assumption may not be. Okay, so that's how we build in randomness into the algorithm. Okay, so coming back here, So what I want when I said expected time is that it should not depend on how the values are distributed. I don't have control over the input values. Okay? So this hx equal to x mod t is a nice uniform hash function if the input values have equal probability of the mod t value being any of the t values. Okay? Otherwise, in the worst case, an adversary, if I choose this function, an adversary may choose a set S where all of them have the same modulus value with respect to t. Then you get a worst case value of t for the running time. Okay? So now the question is, how do I build in randomness into the data structure? Okay, that's what we're interested in. So the strategy is the following. Is the distinction clear? And what we are trying to do in the case of hashing. So think of it as playing a game against adversary. So whatever hash function I tell you, your adversary can make sure that you will spend linear time for search, that the table location will get all filled up. So the strategy is I'm not going to give you a hash function. I'm going to have a family of hash function. Then for an application, I will pick randomly one hash function and then apply it for my insert, search and delete. Okay. Then I will do the average over all these hash functions, not average over my input distribution, average over. Okay. So now the assumption is made into how good your random hash, the randomness which chooses a good hash function. Randomly it picks one hash function, and that the randomization is built into the structure. So the goal is, so let's call it a family these hash functions are going from u to t, where u has this value and t has this value. These are two uniform hash family. For all x in u with two conditions. Probably is that h, I think uniformly I can f h of x equal to I is most 1 over for any I. For all x, y in u, x is not equal to y. Two uniform or two universal. So I have this family f which has a lot of functions from u to t, and I call that a two universal if you pick, suppose I randomly pick a hash function from here, right? Randomly meaning I look at the number of hash functions, throw that side a dice, whatever value comes, I pick that hash function. then if you give me any element and a location I in the table, then X is mapped to I with probability at most 1 over T. So it's playing a role of a uniform hash function, that it doesn't, it looks at a location and an element and throws into any of the locations with equal probability. And similarly, the 2 stands for this pairwise. And if you give me 2 elements which are not equal, that there is going to be a collision there with probability at most 1 over T. Okay. So if these 2 conditions happen, then I call this family of functions a 2 universal family. Okay. Now, if you are not comfortable with this probability business, the way to think about it is that, what does this statement mean? You look at, for an X and an I, look at how many functions here map h of X to I. Right? Each one is a function which maps somebody in the universe to somebody in the some location in the table. Look at how many functions map h of X to I. That's it's supposed to be 1 over T of the total number of functions. Similarly, look at how many functions that does this. That's at most 1 over T times the total number of functions. In fact, that's the way we will prove when we prove. Okay. Now, so there are 2 questions now. First, are there 2 universal family of functions? Right? There must be. Otherwise, no point in defining something which no family satisfies it. That's question number 1. Question number 2 is, if I use a random function from this universal hash family, is that good for my data structure? Both are relatively easy to answer. So let's see. Let's look at the family of all functions from U to T. I claim that that's 2 universal. Okay, this answers the first question. Are there 2 universal family at all? I said, take this U and take a T and look at all functions. Okay, not just one around. All functions from this universe to T. Look at that family that satisfies these 2 conditions. Okay, can we verify that? Is that easy to see? It's not a nice family I want. That's a problem. We'll spend the rest of the lecture about what is nice and how do we come up with a nice family. But I want to show that there is at least one family. That family F, family of all functions. What would be a nice way of representing a function from U to T? Well, for every element in the universe, just say where it's going. Some sort of a representation will just do the job. Right? So let's verify this condition 1, right? Fix X and I. How many functions? Totally, how many functions are there? What is the size of this? How many functions are there from U to T? T power M. Because U is of size 0 to M minus 1, T is of size 0 to T minus 1. Okay. S is the set we want to represent of size N. We will come and connect N with all these parameters. Don't forget N for now. So a number of functions in the family is T power M, is that right? Yeah? Everybody sees that? How do you prove this?
Each one has T choices.
Each one has T choices. Yes. Okay. So let's take the first property we want to show. Fix x and I. Some value x in the inverse and I some table in the T. Number of functions with h of x equal to I. How many are there? T power? Why? So now we need to worry about m minus 1 values. Where do they go? Each one has a choice of t. So t power m minus 1. And that's what I want to show, right? So probability that h chosen at random for any fixed I is at most 1 by t. Right? Out of t to the m functions is actually equal to. So it's not very hard to verify, even though it does look a complicated definition. Can you verify easily the second one also? So let's fix x and y, x not equal to y, and let's fix I also. What is the probability that h of x is equal to h of y equal to I? How many functions have this property? Right, so I have x and y have been fixed to certain value I. So now you have all the choices for the remaining. T to the m minus 2. For a fixed I. For a different I, another t power m minus 2. Right? I am looking for how many of them will have h of x equal to h of y. So, t into t power m minus 2. So that's again 1 by t. T to the m minus 1 functions. Worry about independence here. Okay. This 2 universal is talking about pairwise independence. So once I fix x to be having a certain value, in general, talking about functions, it might affect, without any condition, probability h of y equal to I is 1 over t. But once I fix h of x is I, h of y may change. I mean, in this case it does not. When I look at all functions, it does not change, but in general it can. Okay. So this is a critical independence property, pairwise independence, if you like, and that's the word 2 universal. Okay. In general probability distributions, you may have a value of 1 may decrease, and here we want to say that they are independent. So is there a family of 2 universal hash? Yes, family of all functions, one example. That's not a nice example because I don't like this size for some reason. Okay, I want a small family of 2 universal hash. We will argue that such a small hash family later in the lecture. Now the second point I want to make is that now if I use such a hash family and then I randomly pick one hash function and use it for my data structure about, okay, here is a set, I am trying to use this hash function to insert it into this table. Okay. Now what will happen to the expected size of one location, one bucket? So we'll call this as a bucket. Okay. In the worst case, this bucket can become ordered. Random hash family, hash my elements into this table using that hash function. What can I say about the expected size of the bucket, where the expectation is over what? all the hash functions in my family. That's how I built in the randomness here. So I have a family of hash functions. When I average over all these hash functions, the size of this bucket. It's very hard to verify that. That's pretty reasonable. Let me give a quick informal argument for this claim. If we insert, search, delete using a random hash function from a 2 universal family, then the expected size of the ith bucket for any bucket for any I is at most cardinality of S by 2. It just follows from the first property of the 2 universal family, because what am I doing? I am taking my set S and I am mapping it here, right? So the ith bucket, the expected size would be, this expected size here is one line argument, this is equal to summation I in S probability X Chennai. So right, I pick for every element in S. If it gets into, if h of x is equal to I, then it will be 1 and 0 otherwise. The size of the expected size. Right? I just go every element and say, see, is it contributing to my ith bucket? Well, when will it contribute to the ith bucket? If it gets into ith bucket. If it gets into ith bucket, it will contribute 1, otherwise it will contribute 0 to the expected size of this bucket. And what is the probability that h of x is equal to I? The first condition says that it's at most 1 over t for every element in the universe. So in particular for every element in the set S. Okay. So this is at most content. So t is our choice now. T is a parameter, remember we didn't fix it. T is just a table size. U was a universe, S was the set I'm going to represent of size n. T is my choice now. So I choose T in a way that this is small, right? Because expected size of the bucket is a measure of my search time, insert time, delete time, right? Because how much is the search time? How do you search? I go hash in and go and do a linear search into that size bucket, right? So the expected size of that bucket is my measure of expected time for insert, search, delete. So choose T, and size of the set may keep changing because as you keep inserting, it's a dynamic data structure. So as you keep inserting, the set size is increasing. So you update your table size. So choose T something like order S, 2S, S by 2 or something. Then this will be a constant. So T to be S by 2, let's say. Then the expected size is a constant. So is that's it? That is sort of the answer to my first part of what I wanted to say, that I'm going to come up with a data structure where the expected time for all these operations is constant. So what do? Well, I just do hashing with chaining, and I want to ensure that the expected sizes of these buckets are small. Well, how do I ensure that? I use a nice hash function. Now, to play against any adversary, I choose a family of two universal family of functions, and from there I pick a random hash function and use that for my search. So that hash function is not revealed. I know I'll reveal it that it's one of these functions, but I'm not going to tell you which function. Then when you do the expectation analysis over this hash family or the number of functions, it turns out your times are all constant. Okay. So now what I want to now do is to show you that there is a family, two universal hash family, which is much smaller in size. Okay. So it's more like order m squared is what we want to come up with. That's the first claim we will show. That's a very interesting algebraic construction. And then I'm going to see another application of this for some approximation algorithm. Okay. So this hash family, hashing has a lot of applications. It started off as a solution to solve the data structure problem of dictionary data structure problem, and that's where it's largely applied as well. In practice, when you have compiler, simple tables, various areas where there is nice small hash, interesting hash functions are used, and that's how it's used. Instead of using a complicated balanced binary search tree and spending logarithmic time, when you know a bound on the size of the universe, there are some interest. You can use hashing, simple structure where you may have to trade off a little bit on the worst case running time, but you can implement it. But interestingly, later on, hashing found a lot of applications in other domains, including approximation algorithms. So the next half an hour, I plan to give you a family of functions, two universal family of functions. The total number of functions is much smaller than t to the m, and B, give an application for approximation. Okay, so what we observed here is that if you take all family of functions, then that satisfies these two conditions. Okay, now I want to argue that no, you don't need all of them. I can pull out some subset, a small subset of these functions. That also has this kind of a property that this is this uniformity, and this is the pairwise independence. Okay. And here is the following construction. So what is small sized two universal. First, it's going to be algebraic, so we're going to use primes and fields and so on. Simple property. So we'll assume the universe size is a prime first. Okay, that's an easy assumption. What do you do in general if it's not prime? Go up to the next prime. So I'm going to, you want a function only on this. I'm going to give you a function on this. Okay, you can restrict it to your whatever size you want. So I go to the next prime, which is at most 2 times m. That's where I'm going to define my family. go back to quick sort and get your feel for it. So I talked about this function, right? Basically take the value and do a mod of your table size, and that seems like a very simple function. The problem is that your input may be biased. Okay? So this is similar to, in your quick sort, I can just take the first element as the pivot and partition. Problem is the input may be biased. Okay? So we went to a random pivot. There is also another way to fix it. How do you do? So I am going to do the deterministic quick sort, where I take the first element as a pivot. Okay? But I still want it to work for your input. So what do I do first? I want it to have a flavor of the randomized quick sort. How do you do that? Yeah, that's a good correct answer. How do you do that?
Take any random permutation.
Yeah, so you take your input, some input comes, it may be biased, first randomly permute it. So I apply a random permutation, randomly permute it, now you apply your deterministic algorithm. Okay, and it works well on the average, again under all possible random permutations. Something similar is what I'm going to do. I'm going to take, I like this kind of a function, but it may be biased. So what I will do is I take my input x and apply a random linear transformation on it, and then I apply mod t. Okay, so my h of x this is the linear transformation. I pick a random a, random b, take my x and do a ax plus b. It's like a random permutation. Now do a mod t. So let's call this HKB. The claim is this family F H A B is not equal to 0 A B is 2 units. How many functions are here? P minus 1 into P. A has P minus 1 choices, B has P minus, A has P minus 1 choices, B has P choices. So P square, and that was my claim. I said the number of functions I'm going to get is something like M square. M is the universe size. Okay. So small, much smaller than t to the m we had. This is just p square. Okay. As we know what to prove. You just have to go plug it in and verify these properties. Use certain field properties, inverse, things like that. So it's not very hard. Let's just check. What is the property 1? X and I. How many functions HAB have the property that HAB x equal to I? Well, HAB x equal to I means what? AX plus B equal to I. So I'm interested in the number of solutions A comma B such that Ax plus B equal to I. X and I are fixed. How many pairs A comma B are there such that Ax plus B is I? Right? Now if suppose I fix B, choose some value for B. Then what is A? Choose a value for A. Is that better? Okay. Maybe I need to distinguish between B equal to 0 and B not equal to 0. Number of functions in the family. So what do I want to say? I did not make any mistake. Yeah, so it's not Ax plus B, there is a mod T factor which I ignored. Let's be careful about that. Right, Ax plus B equal to I mod T. Right, that's what it is, right? So I want Ax plus B mod P mod T equal to I. Yeah. So the way to think about this, so you have your universe 0 to t minus 1. When I do mod t, this is a t minus 1, 2 into t minus 1, and so on. Okay, so what do I want to show? Let's write this down, then we work backwards. What I want to show is that at most 1 over t of these functions, right? So t into t minus 1 by t is what I want to show. Right? Total number of functions is p into t minus 1, out of which I want to show the claim of 2 universal first property is that 1 over t of these functions does this. So let's just fix let's compute number of functions h such that h of or ax plus b is equal to some, instead of I am going to call it some r mod p. Let's fix some value r mod p. So r is certain value here. how many so here is my universe, which is 0 to t minus 1. First permutation of the linear transformation, it just takes ax plus b mod p. First of all, ax plus b mod p just transforms things like this. Let's verify that that's true, that if x is not equal to y, implies ax plus b mod p is not equal to ay plus b mod p. In mod p, we haven't come to mod t yet. In mod p, if you have two elements, they get mapped to two distinct values. Okay, that's easy to see, right? Because suppose ax plus b equal to ay plus b mod p, what does that mean? A into x minus y is congruent to 0 mod p. In mod p, that means a is 0 mod p or x equal to y mod p. We assumed a is not equal to 0 mod p and x is not equal to 1. Okay, so ax in mod p, they all go to different locations. It's just a complete permutation. That's what ax plus b is, just doing some random permutation of this universe. Okay. Now, okay, so if I fix a certain value r and say and I fix an x, how many ABs will map x to R? That's this question. How many ABs will map x to R? Okay. So here is what I wanted to say, that if I fix B, then A gets mapped, fixed. Right?
So R can be written as K1T plus I.
We'll come to that later. Mod T, I will come to that. That's exactly what I need the next step. For now, I'm saying I fix a certain value x in my universe and certain value r in the universe. How many a comma b's will map x to r? Okay. P minus 1. Why? For every value of a. Okay, that's a good way to think about it. So I fix a value of a. That means that b is r minus ax. B is fixed. Once a is fixed, b is fixed. So you have choices for a, p minus 1 choices for a. Pick any one of them. Then ax, b is fixed to be r minus ax. So if you fix a and r, so there are p minus 1 choices, right? So this is number of functions h such that ax plus b is p minus 1. Good. This is okay. So now we'll come to mod t, how it's going, right? Now I am interested in how many ABs are there such that ax plus b mod t is equal to I. Okay. So now when I look at mod t, how many values are congruent to r mod t? P by t. Right? Right. How many values are there congruent to r mod t? I fix a value r. How many of them? Because if you break this universe P into mod chunks of size t, each one will have one value which is congruent to r mod t. So there are ceiling P by t values congruent to r mod t. So that's it, right? So now I want to say into P by t. Right? This is the working backwards. So what do? I fix a particular value of R. So I'm saying I want I. This is what I want. I want HABX is equal to I mod T. I is a value in mod T. So there are so many values. So if I is, let's say 5, then in this universe there are so many I's, P by T values which are congruent to that particular value mod T. For each one of them, I have P minus 1 choices of A and B. That will get mapped in. Okay, so that is P minus 1 into P by T, and that's what I want. Okay, the second observation is somewhat similar, very similar actually. Let's number of values in Q congruent to I mod T is at most T by T. Therefore, the number of functions H such that second observation is very similar. What is the second approach? Second thing we need to show this pairwise independence, right? X, Y, X not equal to Y. Suppose h of x equal to HABX. I want to compute. Our goal is to compute the pairs AB such that h of AB of x equal to h of AB. And we want to again claim that it's of NP minus 1. So very similar argument. H of AB x equal to H AB y means what? Ax plus b mod p is congruent to ay plus b mod p whole thing mod p. So again, let's Ax plus b suppose is congruent to R mod p, and Ay plus b equal to congruent to S mod p. Then how many solutions are there for A and B? Suppose I fix an R congruent in the domain 0 to p minus 1 in X. So X plus b gets mapped to R, Ay in this here. So X gets mapped to R, and suppose some Y gets mapped to S. How many ABs are there that can do this? One. This is unique because it's a two linear equations on X and A and B. You solve it, you get a unique value A and B. So there's only one AB which will get mapped X and Y, X to R and Y to S. So now we have to come to this of modulo T. How many pairs R and S R and S are not equal because X and Y are not equal. Okay. So now all we need to analyze is how many pairs R, S are there such that R is not equal to S, but R and S are congruent modulo T. Okay. So number of pairs R, S such that R is in U, S is in U, R is not equal to S, but R is congruent to S mod P. That's the number of ABs that will do this.
That would be P into P minus 1 by T.
Exactly, because you will have P choices for one, and then you will have, because R is not equal to S, you have to pick from the other P by T minus 1 of these columns, and so it's again P into P minus 1. More precisely, T by T ceiling minus 1, and this is at most. Okay, so that's very nice construction, simple algebraic construction, which simply says that. So now it's 2 universal, and the size is pretty much the square of the universe, square of your domain. Now let me spend next 10 minutes giving you an interesting application of this for de-randomization. Let's look at this max 2-SAT problem. Okay. Hopefully you heard about it yesterday, right? Max-SAT approximation algorithm. No? Yes, no? Did Radhesham talk about it? Okay, so let me tell you about it. So here is a formula F, a Boolean CNF formula. Maybe Srijit must have talked about it. He must have talked about satisfiability. Okay. Now, on variables x1 next to xn, each clause has at most 2 variables. It's a special case of CN of SAT. The general CN of SAT is just a conjunctive normal form. You have n's of r's on n variables, and you want the satisfiability problem is this satisfiable? Is there an assignment to the variables that will simultaneously satisfy all the clauses? The max SAT question, the optimization version of this is, what is the maximum number of clauses you can satisfy? Okay. The satisfiability question algorithm might say yes, it's satisfiable, or not, no, it's not satisfiable. If it's a case of no, I want to know what is the maximum you can satisfy. Okay. This is an optimization version of it. Now this is NP hard even for 2-SAT. Okay. If every clause has at most 2 variables, checking satisfiability can be done in polynomial time. Is it satisfiable or not? There is a nice simple polynomial time algorithm. But if I ask you, in the case of no, what is the maximum number of clauses you can satisfy? That's an NP hard problem. Okay. Now we want to design an approximation algorithm for this. Given that it's NP hard, I want to come up with an approximation algorithm which will satisfy as close to the optimum as possible. And I want to improve on this approximation ratio. Okay. So this is a very simple randomized approximation algorithm. So I'm trying to look for an assignment to the variables. So what is the simplest random assignment you can think of? every variable should take value 0 or 1.
So random
So just randomly, toss a coin, the probability half, uniformly at random, every variable I set it to 1. If there is a head, I'll set it to 1, if there is a tail, I'll set it to 0. Now we want to understand the number of satisfied clauses by this random assignment. Okay, but since it's a randomized algorithm, we can only talk about the expected number of clauses you can satisfy. Right? So what is the expected number of clauses you can satisfy? Given any clause Cj, let's sorry, I'm going to make an assumption that every clause has exactly 2 variables. That's not a very hard assumption. You can create some dummy variables, and if there is only one variable, you can just add some new variable and create some other things. So suppose every clause is exactly 2 variables. Given any clause Cj, what is the probability that Cj is satisfied? Why? What is the probability that it is not satisfied? Well, both variables get value 0. Then only it's not satisfied, and that has a probability of half into half, 1 by 4. Half into half, and here, okay. Pairwise independence, I'm using it here because these variables are set independently. So the fact that this is 0 does not affect the probability that this is 0. So as 1 by 4 is the probability that this clause is falsified. So 3 by 4 is the probability that C is satisfied. Therefore, expected number of clauses satisfied by linearity of expectation is 3m by 4, because take any clause, there are m clauses, pick any clause, the probability that will be satisfied is 3 by 4. So add them all, you get 3m by 4.
But these clauses may not be independent.
Yeah, but the argument, so linearity of expectation does not require independence. If you have x1, x2, x3, xn variables, each has a certain probability, then the expected number of values is sum of the expectation. Linearity of expectation doesn't need any independence. E of summation xi is equal to sum of E of xi. Okay. So I have a randomized algorithm which will satisfy 3/4 of the clauses, and the maximum you can satisfy is all the clauses. So it's a 3/4 approximation algorithm. Right? It's at least 3/4 of the optimum, because the optimum can be m. Okay. So now I want to de-randomize this algorithm. I want to get rid of this randomization, somehow come up with a deterministic algorithm which will give you a deterministic assignment which will satisfy at least 3/4 of the clauses. Okay. Yeah. Now you both, Ayush and Ramnath, are going to talk about the satisfiability and different de-randomization procedure when you talk about next week. But here I'm going to talk about one way of de-randomizing using this 2 universal hash family. Okay. So you're going to talk about a different way of de-randomizing using what is called the method of conditional expectations. Okay. So let's stare at this result. What is this saying? Probability expectation is all about averages, right? So let's just interpret this statement in terms of averages. What is this saying? This is saying, look at all 2 power n assignments. Right? When you say setting uniformly at random and then the expectation, all that means that you look at all 2 power n assignments. For every assignment, compute the number of clauses satisfied, take the average. That average is 3m by 4. That's what this is. This is exactly what it's saying. Right? So I have this 2 power n assignments to all the way to 1, 1, 1, 1. For each of these assignments, I compute number of satisfied clauses. And divide by 2 power n. That average is 3m by 4. This is exactly what this means. You know, inside this whole probability analysis, that's what's going on. Okay. Since the average is 3m by 4, there must be some assignment that should satisfy at least 3m by 4. Right? Is it no, it's not possible that you have average, you know, of the marks is 87, but nobody got greater than or equal to 87. That's not possible. If everybody got less than 87, the average will be less than 87, right? So since the average is 3m by 4, there must be some assignment that satisfies at least 3m by 4. And how do you find that? Using method of conditional expectation is what you will talk about next week. Okay. So, but all we know is there is some assignment which satisfies at least 3m by 4. I want to find that. Okay. Now let's again carefully look at what we used in this analysis. Well, what did we use? This is the crux of the analysis, right? I had two variables, you know, xi, xj, in a clause, and I want pairwise independence here. The probability, I want some distribution where the probability that this is falsified, the probability that xi equal to xj equal to 0, I want this to be 1 over 4. Right? Any kind of assignment where I have these two possibility that probability that xi equal to 1 is equal to probability that xi equal to 0 equal to half. This is one thing I used. The second condition I used is that probability that xi equal to xj equal to 0 is the most one. If I have some way of assigning 0 1 values to these variables, satisfying these two conditions, this entire analysis will go through, and this average argument will go through, and you know, in that set there is some assignment that satisfies at least is also clear, right? So now this is what I'm going to do. Magic, right? Assignment is a function. A 0 1 assignment for these variables, what I want is I want a function which takes values 0 to n minus 1 in n variables and gives me a value between 0 and 1. An assignment is, you know, for every variable I need a value 0 or 1. Okay? So now I'm going to use this as my universe and this as my table. Okay? So I mean universe extended to your next prime and so on. And use this two universal hash family. How many functions are here? P square. So in our case, my universe is n, there are n square functions are there. Okay? So I'm going to look at this is order n square because I have to go to the next prime or something. Okay. So each hash function is an assignment, 0 1 assignment to n variables. Think of it as a 0 1 assignment to the n variables. And what are the properties I know? The fact that it's two universal means that I know that my t, what is the value of t? 2. Table size is 2. So the probability that for a variable it's going to give a value 0 is half. For a variable it's going to give a value 1 is half. That's the first condition I wanted. And if you pick two variables I and j which are not equal, then probability that both are going to be the same is at most 1 by 4. Right? I want over m. Again, it's 1 by t again, half. When they both are equal, is at most half, but that means that you can also verify here that they both are equal to 1 with probability quarter, both are equal to 0 with probability quarter. And I really need that this is what I want. Okay. So to summarize, what I'm saying is, instead of trying over all possible 2 power n assignments, try over these n square assignments. Think of each function in the 2 universal hash family as an assignment. Try over these n square assignments. The fact that it's 2 universal means that this argument will go through, which means that among these family of assignments, the average is at least 3m over 4. So there is some assignment in this family which will satisfy 3m over 4. Deterministically find it. There are only n square functions. Try one by one. Take this assignment, plug it in, compute the number of clauses satisfied in n square time plus whatever time you need to check for assignment. So deterministically you can actually find an assignment that satisfies 3m over 4 clauses, at least 3m over 4 clauses. This is a way to de-randomize it. Is that clear? So now this whole thing, whole argument can be extended to Y2 SAT. If instead of had K SAT, then you have a different kind of probability here. 1 minus 1 by 2 power k or something. You have that many number of clauses. Now you need what is called K universal, because you need K-wise independence, because when I look at a clause, I want to make sure that they are K-wise independent, so probability that they all become 0 is at most 1 by 2 to the K. To argue that, I want to argue that setting this and this and this and this does not affect this. So that's this K-wise independence. So there is this K-wise family of functions that can all be used to de-randomize. So this is a very nice tool to de-randomize. I'll leave you with one exercise, very similar. Instead of max 2 SAT, look at max cut. So it's a max cut problem. I have a graph. I want to split it into 2 parts such that lots of edges go across. I want to maximize the number of edges that go across. This is a max cut problem, NP hard. It's a very similar approximation algorithm. Everything goes through. So for every vertex, I randomly decide I put it in this part or that part, the probability half. Now put it that way. Compute the expected size of the cut. Okay, and you can argue by I pick an edge, what is the probability that it will be in the cut. So you can compute the expected size of the cut, and you can de-randomize it exactly by using 2 universal hash families. Sorry? Yeah, max cut can be converted to max up. Not just exactly the way you said. It requires a little bit more work. So what are the clauses? What are the variables? You need to figure out. Yeah. You can convert it into 2 SAT and max.
So every path can be a clause.
Every path. Think about it. Okay, but you can use that directly. The entire argument goes through for max cut to get a half approximation algorithm. Okay, so to summarize, you have this 2 universal hash family, which can be used for solving the dictionary problem, but a small size 2 universal hash family can also be used to de-randomize randomized algorithms. Wherever you have pairwise independence and uniformity is used, you can use this family, run deterministically, because it's, so this is where the small size was important. I could not have used if I had t power n, in this case it's 2 power n. If I'm looking at 2 power n functions, then that's not a good way to de-randomize. I can't run them through each of these functions. If fact that there is a nice n square size family helps you retain n plus n.